Alright, so now in this video we're going to put our efforts towards this concept known as the work-energy theorem. This is a very big important theorem, and so the net amount of work done on an object, right, let's start that again. So the net amount of work done on an object equals that object's change in kinetic energy. And so this is what we know as the work-energy theorem, right? So Theorem, okay? And so basically mathematically it's just a simple relationship. So work equals change in kinetic energy. And so if I want to expand this out, that's going to be F delta X equals 1/2 m v squared minus VO squared. I like to write it like this because it helps with the solving later. Especially if you have to do anything along the lines of solving for like final velocity or initial velocity. It just makes it easier because at some point in time you would factor out the 1/2 times mass. Now, one of the multiple choice questions that they do like to ask is, what does work equal? And two of the answers will be K and delta K, right? And so the theorem says it equals change in kinetic energy, but this is the trap. Because what happens is, if I start from initial velocity, or if I have initial velocity of 0, my work does equal kinetic energy, but it equals final kinetic energy. And so it technically is a change, right? That's only because my Ki, or my initial kinetic energy, would be 0. So it's like Kf minus 0. It's just going to be simply Kf. So don't fall into the trap, right? And so remember, the answer would be change in kinetic energy. So what this actually allows us to do is redefine work in terms of energy. And this is the basis of our unit here, right? And so we talked about in the first video of this unit, talking about that it's we're going to talk about transferring a quantity. And so this is what we're transferring. So what happens is, work is the process by which any force, or a force, transfers energy into or out of a system. And so earlier we talked about how work can be positive, it can be negative, or it can be 0. This is the application of that. So if work is positive, that means I'm going to transfer energy be transferred into the system, right, causing my energy to increase. And if it's negative, right, energy is actually transferred out of the system, and so that means that my energy will decrease. And if it's 0 work or no work done, then we don't have a transfer, okay? And so remember, each force that performs work is the means by which an energy transfer takes place. All right. And so another way we think about this work-energy theorem is also to say that work is equal to the change in energy. Okay, so it's not necessarily just kinetic energy, but it's actually the change in all energies. And so kinetic energy is just the easy part, because if I'm applying a force, you understand that forces accelerate, right, and they cause changes in motion, which means it changes the velocity, changes the kinetic energy. So conceptually, the work-energy theorem does make sense, right? And this idea that if I'm doing like no work, right, then there's no changing energy. So if the speed is constant, and that means that if v equals v0, which basically means I don't have a change in velocity, right? Well, what does that mean? My delta K is 0, which then ultimately means my work is 0, right? So I'm not transferring any energy into the system if I'm at a constant velocity. Remember, constant velocity means acceleration is 0, right? And so what does that mean? Your net force is 0. But ultimately, what does that mean? There's no work being done, which means there's no change in kinetic energy. So here are just a couple example problems, right, around this work-energy theorem. Or actually just one example problem here, broken up into 3 parts. So a car with a mass of 1,300 kilograms is traveling on a level road as it comes around a circular shaped curve. The car moves along the curve with a speed of 16 meters per second. That car travels a distance of 20 meters as a centripetal force of 1,600 newtons provided by static friction acts on the car. How much work is done on the car as it rounds the curve? So remember, in AP Physics 1, we always assume uniform circular motion, which means your speed is constant. So as it rounds the turn, there is no work being done, right? Because the speed is constant. Now, what happens when we do change the speed of the car? So if the car in the previous question were to decrease in speed from 14 meters per second, how much work would be done on the car? And so now we apply our equation. So work is equal to change in kinetic energy. So it's 1/2 m v squared minus vo squared. Okay. If we just do a little prediction, notice that our final velocity is going to be less than our initial velocity, which means we should have a negative change in kinetic energy, which means we ultimately did negative work. And so if we just want to prove that numerically, so we have 1/2, okay, times 1,300 times 14 squared minus 16 squared. Okay, and so we end up with 0.5 times 1,300 times 14 squared minus 16 squared. Again, when you do this, plug this into your calculator carefully, because it all depends on where you put that, where the 14 squared minus 16 squared comes into play. And we find that there was negative 39,000 joules worth of work. Okay, and again, that matches our prediction that we should get a negative number because we are taking out energy in the system. Okay, now what external force is going to account for all this work, right? Or the removal of energy. So notice up here we talk about static friction. So it's not going to be that, because static friction applies to that the car is not going to skid or slide into or out of the circle, but the wheels are moving, right? And so what force could be present? Well, the kinetic friction, right? The friction between the tires and the road is one possible external force, right? Another one, which there could be a braking force, right? What's one way that you can do this with a car? Well, you can brake the car. The other one is the one oftentimes we neglect. That could be air resistance, right? Our cars, we want them to be aerodynamic, but in actuality, a lot of them are not aerodynamic. So there is a built-in air resistance to the car, and so that's it for work energy theorem, right? And so understand that you can, there are more example problems or more problems where you can have to find the amount of force, or you may have to find one of the velocities or one of the speeds. Okay, so from here on out, we're going to look at start turning this into a conversation about conservation of energy. First, we're going to talk about we're going to talk about the different potential energies.